With the explosion of the New Glenn rocket last week, Blue Origin's rockets and lunar landers will be out of NASA's Artemis moon plans for some time, possibly a year or two. This leaves NASA in a precarious position, almost entirely dependent on SpaceX and the Starship vehicle to deliver crew and heavy cargo to the lunar surface. Did it have to be this way? In this video, I want to examine NASA's approach to returning to the moon and contrast it with China's slow and steady strategy, which continues to deliver one success after another. So far, China has chosen to use flight-proven technology that's well understood, resulting in highly reliable systems. In contrast, many US vendors are working on high-performance systems that rely on risky, unproven technologies. The Chinese Long March family of rockets uses liquid oxygen and kerosene, the same propellants as SpaceX's Falcon 9. The engine cycle is a gas-generator design, a reliable and well-understood piece of technology. To be fair, the upcoming Long March 10 will use liquid hydrogen on its upper stage. This performance boost is necessary for China's crewed lunar missions. In this video, I will argue that NASA should strongly prefer vendors using simple and reliable technology for all critical Artemis activities. A clear bias towards flight-proven, reliable systems gives the Artemis lunar base plans the best chance of success. After watching, let me know your thoughts in the comments below, and we'll discuss them in the live stream this Saturday. NASA's critical path activities should prefer simpler technology. A strong bias towards high reliability over high performance is what's missing from NASA's Artemis objectives. Right now, NASA has no real opinion on the kinds of technologies its vendors use to support the Artemis program. I think this approach is wrong. As a result, many of NASA's contractors are choosing complicated, high-performance systems that carry serious failure risks, as we saw last week with the Blue Origin explosion. Does NASA require complicated, high-performance systems to return to the moon? No. Neither Apollo in the past nor China today are using high-performance systems to return to the moon. It's entirely possible to use lower-performing but far more reliable systems. During the Apollo era, manned missions flew between 2 and 4 times per year between 1968 and 1972. In contrast, there has been a 4-year gap between Artemis 1 and Artemis 2. All engines on the Saturn V use the gas generator cycle, while the command module and the lunar module used even simpler pressure-fed engines. All in-space operations relied on storable propellants. Only the Saturn V used cryogenic propellants, and only on the upper stages. Today's human landing system vendors, by comparison, are using cryogenic propellants on the landers themselves, along with much more complex engine cycles. Complicated engine cycles come with more failure modes, which almost inevitably lead to rapid unscheduled disassembly. When that happens on a fully fueled vehicle, the consequences can set a company back by years. The complexity isn't needed. The United States proved that with the Apollo 11 mission in 1969. The Chinese are also successfully reaching the moon using simpler and more reliable technology. With last week's major setback for Blue Origin, a critical NASA vendor, it now looks increasingly likely that the United States will not return to the moon for some time, possibly not before 2030. NASA's complicated multi-launch moon missions. NASA's selected vendors for human missions to the moon, SpaceX and Blue Origin, both rely on high-performance cryogenic propellants. This approach requires multiple refueling missions before the stack can head to the moon. The more launches required for a single mission, the higher the chance that something goes wrong, due to delays, scrubs, or outright failures. High payload rockets demand high-performance systems to lift heavy mass into orbit and then push it towards the moon. This, in turn, requires extreme conditions inside the engines, very high temperatures and pressures. In contrast, China's simpler, slower, and more incremental approach allows its rockets to fly with high levels of reliability. This has resulted in an impressive number of successful lunar missions, including several that collected and returned the lunar regolith samples. Let's look at 2 critical aspects that highlight why simplicity and reliability should take priority over raw performance and payload capacity. Engines, boring versus high performance. Both SpaceX and Blue Origin are developing high-performance engines. Eventually, this will lead to lower launch costs for commercial missions and more mass delivered to the moon and deep space. However, in the context of a race back to the moon, these complicated engines will take longer to reach the high levels of reliability and flight cadence that NASA needs. What about using boring engines instead? That's exactly the approach Sir Peter Beck, CEO of Rocket Lab, is taking. Beck has a clear preference for reliable, straightforward engineering over flashy complexity. His focus is on rapid iteration, high reliability, and fast turnaround. After all, the vast majority of missions are volume constrained, not mass constrained. Optimizing for maximum mass to orbit is often a waste of time for most missions. For example, even SpaceX's transporter missions, which sometimes carry over 100 satellites, usually have a total mass of around 5,000 kilos, while the Falcon 9 can lift over 20,000 kilos. Beck's boring but works philosophy is paying off. Rocket Lab currently has the second highest flight cadence of any American launcher and a flight success rate of over 95%. Rocket Lab rejected hydrogen and complicated engine cycles in favor of a highly reliable vehicle, even if its mass to orbit performance is lower than some rivals. In the small launch market, Rocket Lab reigns supreme, even though its 300 kilo payload to orbit is lower than Firefly Aerospace's Alpha rocket. That's because Electron has now flown over 80 times, compared to just 7 flights for Alpha, of which only 4 were successful. It turns out a simple gas generator engine is all you need. Let's turn to another key factor for achieving high cadence: the choice of fuel. Propellants, storable versus cryogenic. Building a moon base from scratch requires a large number of launches on rockets that are reliable and can fly often. Let's break propellants down into 3 main categories: storable propellants, mild cryogenics, and high-performance cryogenic fuels. Storable propellants. These fuels can be stored at room temperature, don't boil off, and provide instant, reliable restarts. They require simpler tanks and ground support equipment, which leads to streamlined operations and faster ground processing. It's worth noting that many successful moon landings, both crewed and robotic, have used simple pressure-fed engines with storable propellants, including Firefly Aerospace's recent Blue Ghost landing. Liquid methane, liquid natural gas, or Methalox. Stepping up in performance, we move to cryogenic fuels. Liquid methane is currently popular among space companies. Blue Origin uses it on New Glen's first stage. SpaceX uses it on Starship, and Rocket Lab is using liquid natural gas for Neutron. Several other startups, such as Relativity Space and Stoke Space, also plan to use liquid methane. In practice, even when companies say they're using methane, they often mean natural gas. The performance penalty is very small, only 1 to 3%, so that's what most companies actually fly with, despite what their websites might claim. Liquid hydrogen or Hydrolox. The highest performance fuel for a chemical rocket is hydrogen. It delivers the best fuel efficiency, but it greatly increases complexity, not just in the engine, but also in ground operations, logistics, and overall mission planning. Hydrogen is notoriously difficult to handle. It requires extensive chill-down procedures, constant boil-off management, large safety exclusion zones, and highly specialized ground support equipment. As we've seen with repeated delays to Artemis launches, hydrogen can leak through almost anything, frequently causing scrubs. This is exactly what you don't want when trying to maintain high launch cadence for a moon base. In addition, if you need multiple flights in quick succession for orbital refueling, a single hydrogen-related scrub could ruin the entire mission by causing the Earth and Moon to fall out of alignment. Using hydrogen potentially severely impacts reliability and launch cadence in exchange for higher payload performance. 3-ton lunar landers, Impulse Space versus Blue Origin. Let's examine 2 different lunar landers, both capable of landing 3 metric tons to the lunar surface. The first is Blue Origin's Mark 1 lander, and the second is the upcoming lander from Impulse Space. While both can deliver the same payload to the lunar surface, their technologies are very different. Blue Origin chose a high-tech, high-performance, and high-risk approach of using liquid hydrogen on both the New Glenn upper stage and the lunar lander itself. Impulse Space, on the other hand, chose to upgrade an existing rocket engine already proven to work reliably in space. In addition, their use of green, storable propellants results in simpler handling, logistics, and ground operations, long loiter times in orbit, and less extreme conditions inside the engine, all of which contribute to higher reliability. Storable propellants also boost flight cadence. They can sit inside a payload fairing for days or even weeks in case of bad weather or other delays, without the need for destacking, something that would be required for a cryogenically fueled lander. Blue Origin's BE-4 engine, used on both New Glenn and Vulcan Centaur, is an oxygen-rich stage combustion engine. It's a complicated cycle that requires very high temperatures and pressures inside the engine. The hot oxygen is highly reactive and can cause ignition or corrosion of components. Any deviation in component alignment or specifications could lead to catastrophic failure. Precise control of multiple fluid paths, high-speed turbo machinery, and sophisticated thermal management are all required for the engine to function correctly. Highly complex engines generally lead to lower reliability, as there is very little margin for error in the components. Let's contrast that with the Impulse Space lunar lander stack, which uses the Falcon 9 as its launch vehicle, with Falcon Heavy likely needed for heavier payloads. The Falcon 9 is a highly reliable launch vehicle, and Falcon Heavy has also flown successfully several times. While Impulse Space's Helios space tug is not yet operational, it is based on an engine and propellants already flown in space. Helios uses a cryogenic propellant, likely liquid methane with a gas generator engine. The lander itself uses a storable propellant with no boil-off risks or the complicated handling requirements of liquid hydrogen. Impulse Space plans to offer 2 rideshare missions to the lunar surface starting in 2028, with each mission capable of landing 3 tons of payload. By the time Blue Origin is ready to fly lunar cargo missions, it may well face serious competition from simpler, more reliable landers with the same payload capacity. As Rocket Lab has shown with Electron, payload mass isn't the key to success, reliability is. Let's examine operational cadence next, as it is essential for a successful moon-based project. Operational cadence, logistics, and ground support. Storable propellants, especially green or non-toxic ones, are much simpler to handle. The equipment and machinery required are easier, cheaper, and more readily available. In the case of launcher-agnostic landers, like those from Impulse Space, any problems with a launch pad can be easily solved by switching to a different provider. For example, Impulse could launch a lunar mission on a European Ariane 6, a Japanese H3, or even an Indian launcher. Once more American medium-lift vehicles enter the market, even more options will become available. Blue Origin, in contrast, faces much more complicated ground support operations due to its use of liquid hydrogen. This would make it very difficult to launch the Mark 1 lander from SpaceX's Falcon 9 pads, for instance. SpaceX's launch teams do not currently have the equipment or experience to handle liquid hydrogen, and they may not even want to fly such a vehicle given the risk to their operational launch pads. Launching the Mark 1 requires installing specialized support equipment, including new liquid hydrogen storage tanks and transfer lines, cryogenic chill down and recovery systems, and additional safety infrastructure to manage hydrogen's high flammability and tendency to cause metal embrittlement. It's likely that SpaceX or other launch providers would choose not to support launches of the Mark 1 or other hydrogen-powered lunar landers. Why risk damaging an operational launch pad for a single payload when you already have a busy launch schedule? The risks and effort involved in handling hydrogen are simply not worth it for launch providers who don't use this fuel in their own vehicles. Disaster recovery perspective. Sometimes accidents happen. It's worth examining disaster recovery to help us decide the best approach for achieving a high flight rate. The recent explosion at LC-36, Blue Origin's launch pad, is a clear example. Blue Origin is now likely facing a prolonged outage, as their launch pad appears to have suffered extensive damage. The transporter erector launcher and one lightning tower were destroyed, with the other tower also likely needing to be torn down. Damage to storage tanks, transfer lines, and other equipment will require significant costs and repair time. If the root cause is eventually traced back to the engines, the time to fully recover could stretch into many years. Even after repairs are complete, it could take multiple successful flights before confidence is restored, especially given the complexity of the engines and the difficulties of safely handling liquid hydrogen fuel. For Cadence-Focused missions, simplicity beats peak performance. This is why, in my opinion, NASA should not be agnostic about technologies. The technology choices vendors make directly impacts NASA's ability to execute on its moon-based plans. Going forward, NASA should have a strong preference for selecting vendors for critical path missions who use highly reliable, well-understood technologies rather than high-performance but risky ones. NASA should create 2 lanes for Artemis missions, critical and non-critical. For missions that are essential to the success of the moon base, simple and reliable systems should be strongly preferred. For non-critical missions, more risky technologies can be used. Once those systems have proven over time to be highly reliable and capable of frequent flights, they can be moved into the critical lane. NASA needs to stop being technology agnostic. Risky systems are more likely to lead to catastrophic outcomes, which ultimately harms NASA's long-term goals. Final thoughts. In nearly every important criterion for building and supporting a moon base, simpler and more reliable technologies are superior. The one exception is raw performance per launch, where high-performance vehicles have the advantage. For everything else, including reliability, operational cadence, handling and logistics, and resilience to disasters, simpler, well-understood technology is the better option. NASA needs to mandate these reliable systems for critical path missions. The agency's goal is not to provide a pathway for high-risk technologies, it's to build and sustain a moon base. In summary, NASA's moon base objectives are not aligned with its current disinterested approach to vendor technologies. Should NASA prefer simpler and more reliable technologies for critical path moon missions, or should it leave the decision to the market? Let me know your thoughts and opinions in the comments section below. Thanks for watching. If you enjoyed this space video, consider buying me a coffee to help fund more episodes like this. The link is in the description. Watch the weekly live stream to see the images, clips and slides from this week's videos. It's a live Q&A on this week's space topics, where I read out some of the best comments. The more people join, the more fun the live stream is. Be sure to like and subscribe so you will see our upcoming videos. We make videos every week covering the space industry with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.